Welcome students. So in the previous video we have studied the formation of PN junction, and before study the PN junction we have studied that drift current and diffusion current. So drift current is the flow of current due to the external applied voltage or electric field is called drift current, or diffusion current is the flow of electron due to the concentration gradient of the charged particle is called diffusion current. Then हम लोगों ने पढ़ा था फॉर्मेशन ऑफ पीएन जंक्शन, तो उसमें हम लोगों ने देखा था कि when p टाइप ऑफ सेमीकंडक्टर एन टाइप ऑफ सेमीकंडक्टर को अगर डिफ्यूज कर रहे थे तो कैसे पीएन जंक्शन का फॉर्मेशन हो रहा था. मींस अगर हम पी टाइप और एन टाइप सेमीकंडक्टर को डिफ्यूज करते हैं तो वी नो दैट इन एन रीजन इलेक्ट्रॉन्स आर इन मेजॉरिटी इन नेचर एंड इन पी रीजन holes are in majority in nature. So there is concentration gradient among the n region and p region. So due to the concentration gradients, electrons क्या कर रहा था, move कर रहा था n region to p region. If the electron will be moved from n region to p region, then positive donor atom leave कर रहा था in n region, and which is accumulates at the boundary of the PN junction and in n region. Similarly, अगर electron move करेगा in p region, then negative acceptor ion will be accumulate at the boundary. So this is the wall of the positive donor ions and in n region and negative acceptor ions in p region. So this will make depletion layer. Depletion layer का formation हो रहा था, depletion layer, and this is called depletion layer. Depletion layer. We know width of the depletion layer depends upon the doping of the either n-type semiconductor or p-type semiconductor. If the doping level is high, means more number of free electrons or holes will be present in either n region or p region respectively. So if the more number of the doping level is high, then width of the depletion layer is less. So the width of the depletion layer depends upon the doping of the n-type semiconductor and p-type semiconductor. So from this animation we can easily observe that when the electrons is moving from n-type to p-type, and walls of the positive donor and walls of the negative acceptor will be formed, and that is called depletion width. That is called depletion width. In depletion width there is no free charge available. So depletion layer acts as a insulator or isolator between n-type semiconductor and p-type semiconductor. We will study as the forward bias voltage increases, depletion width will be decreases, and current will electrons starts flowing from n region to p region. As in reverse bias, as the reverse voltage increases, depletion width also increases, and diode acts as a open circuit. And in forward bias, diode acts as a short circuit. So this is the theory of the PN junction. Now, so this is the n region n-type semiconductor. This is the p-type semiconductor. In p-type semiconductor, holes and negative acceptor ions are present, and in n-type semiconductor, electrons and positive donor ions are present, and depletion layer is formed at the PN junction. So this is the depletion layer, and width of the depletion layer depends on the doping of the n-type semiconductor or p-type semiconductor, and potential barrier is developed across the depletion layer. This potential barrier opposes the flow of electron due to the diffusion. It opposes the flow of electron from n region to p region. So if the potential barrier opposes the flow of electron from n region to p region, so this area around the PN junction is called depletion layer. So this region is called depletion layer. Since in depletion layer, from this diagram we can easily observe there is no free charge available in the depletion layer. Only two types of the ion present. One is positive donor ion and other is negative acceptor ion. Since this is the positive the negative acceptor ion which repels the electron, and this is the positive acceptor ion which repels the hole. So that's why due to this negative acceptor ion and positive donor ion, electrons will not cross the p-n junction. So this is the voltage, potential voltage. So we know direction of the electric field is from high to low. So this is the direction of the electric field, and we know force upon the charge is QE. So where Q is the charge of electron, and we know charge of the electron is negative. So direction of the force and electron are opposite to each other. Here electric field is induced electric field. So direction of the force and induced electric field are both opposite to each other because polarity or charge upon the electron is negative. So if the direction of the electron is from N region to P region, then direction upon the force is from P region to N region. So due to this force, it opposes the flow of electron because it has a force acting in opposite direction to the flow of electron. So if the force is equal to the force upon the electron, then electron cannot move from N region to P region. Now this is the symbol of diode. So this is the p-type semiconductor and this is the n-type semiconductor. So the p-type semiconductor, n-type semiconductor, this is the depletion region between p-type semiconductor and n-type semiconductor. Since there is no free charge available in the depletion region, that's why depletion region acts as an insulator between p-type semiconductor and n-type semiconductor. So from this animation, we can observe this is the p-type semiconductor, n-type semiconductor diffuses. Then electron will be moved from n-type to p-type and it leaves positive donor ions and in p region negative acceptor ions, and due to that potential barrier is developed at the depletion layer. So these both semiconductor diffuses, then electron move from n-type to p-type, then depletion layer is formed and potential barrier is developed across the depletion layer. Now potential barrier. So potential barrier in the p-n junction diode is the barrier in which the charge requires additional force for crossing the region. In other words, barrier in which the charge carrier is stopped by the obstructive force is known as potential barrier. So due to the potential barrier, charge will not move from n region to p region. So that's why its name is barrier, because it opposes the flow of electron. Depletion region acts as a barrier and opposes the flow of charge carrier from N region to P region. The value of the barrier potential lie between 0.3 to 0.7, depends upon the material used. So if the diode is made of silicon, then its value of the potential barrier is 0.7, and if it is made of germanium, then its value is 0.3. So the value of the potential barrier depends upon the type of material. For the silicon, its value is 0.7, and for germanium, its value is 0.3. Now we can bias the diode in two conditions. First is forward bias and second is reverse bias. If there is no external voltage applied across the diode, then that condition is called unbiased diode. So if there is no external voltage applied across the diode, then that condition is called unbiased diode. If we apply the voltage across the diode, this is the symbol of the diode, and this is the battery, and this is the P type, P terminal, this is the N terminal, and this is the battery. This is the positive terminal, this is the negative terminal. So if we connect positive terminal of the battery to P type semiconductor and negative terminal of the battery to N type semiconductor, then that connection is called forward bias condition. Means if we connect positive terminal of the battery to P type semiconductor and negative terminal of the battery to N type semiconductor, then that bias is called forward bias. Just in opposite, suppose this is the diode and this is the battery, this is the minus, this is the plus, this is the P type semiconductor, and this is the N type semiconductor. So if we connect negative terminal of the battery to P type semiconductor and positive terminal of the battery to N type semiconductor, then that bias is called reverse bias. So this is forward bias and this reverse bias. So this is the forward bias and this is the reverse bias. So this is the zero biased or unbiased. So in this case, there is no external voltages applied across the diode. So in this case, built-in potential, the other name of the potential barrier is built-in potential, is 0.3 to 0.7. For the germanium, it is 0.7, and for the silicon, it is for the silicon, it is 0.7, and for the germanium, it is 0.3. Now, forward bias and reverse bias we will discuss in the next video. Thank you.